Dos.
Muy buenas tardes a todos. Vamos a tener en el día de hoy la sexta sesión del ciclo de conferencias con el profesor Peter Molnar, dado que en la anterior oportunidad la sexta sesión del ciclo de conferencias con el profesor Peter Molnar, dado que en la anterior oportunidad no se alcanzó a terminar el tema, él ha agregado un material de tal manera que lo que tiene que ver con New Zealand será visto en la próxima sesión. Esa es la razón también por la cual no se envió ningún material adicional, toda vez que quedaría ya involucrado en el tema de hoy los papers que se enviaron con suficiente anticipación. Hi Pete, welcome again to our presentation. Thank you very much.
And thank you, Hector. And I understood that Hector told you that because I didn't finish last week, I wanted to add some material, I will not talk about New Zealand. And so today, what I want to do is, again, consider the vertically averaged rheology of the lithosphere. So I'm not worrying about differences in the vertical structure, and ask the question, what sets the horizontal scale of large-scale deformation of continental lithosphere? And this will be maybe more mathematics that some of you want. I hope I will explain it, and if you're patient or if you want to take 10 minutes and wait, I will eventually get back to simple explanations. And at the end, I want to just introduce seismic anisotropy, because seismic anisotropy provides a strain gauge that allows us to address these questions of deformation of continental lithosphere. So I'm drawing in large part from a paper by England, Hausman, and Sonder from 35 years ago, where they considered a region, and they broke it. It appears it's just a block in this case, where in one case they indented one side and they pulled the other side apart, but they have reflection on the boundaries here. So this indentation would be symmetrical. It would continue and then be extension over here. And again, this would continue and go on and on forever and ever. So one can write the boundary condition where v is the component of velocity in the y direction, this is y, x is horizontal, is simply a cosine function of the x position times some constant. And then the other situation would be where the boundary would be strike slip, where you drag the edge of the region along with, again, a sinusoidal function describing the magnitude. So you have a u0 sine, again, with lambda being a wavelength. This is looking at only half a wavelength. So there's a mirror image that would come off to the left and a mirror image that would come off to the right, and this would go on for infinity. So I'm going to derive this for the very simplest case and then jump to a more realistic situation. So we start with the equation of equilibrium. Gradient in the stress tensor plus the body force is 0. We're only in 2D, we're not in the y direction. So this is a vector equation, but there are only two components. The body force is perpendicular to the x and y direction. So the gradient in the horizontal compressive stress in the x direction plus the y derivative of the shear stress perpendicular plus the z direction of the xz component, this sums to 0. That's one of these three equations. There's no body force. And the same with the y component, the x direction, the derivative in the x direction of the shear stress plus the y direction of the compressive stress in the y direction plus the vertical component. But we're not going to worry about this term. We're going to assume no z dependence, not only no z stress, but no z dependence. And so then we consider a simple viscous fluid like the Earth's lithosphere. I realize many of you would not think of the Earth's lithosphere as being a simple viscous fluid, but that's the way I'm going to treat it. U and V are the x and y components of velocity. Eta is the viscosity, and P is the pressure that's due to flow. And if this pressure is a surprise to you, think about a corner kick in football, where the ball is put in the corner and you kick the ball, and the ball can go into the goal because the pressure due to the spinning ball, is greater on one side of the ball than the other. So this is a pressure in situations like that. It's called a dynamic pressure. You could call it a dynamic pressure, but let's not worry. So we define the horizontal compressive stress as 2 times the viscosity times the horizontal component of the compressive strain plus the pressure. And this horizontal component of compressive strain is simply the gradient in the speed, in that component of speed, du dx. The same for the y component. Again, it's 2 times the viscosity times the yy component of compressive strain rate plus the pressure. And so we write it this way. And finally, the shear stress on vertical planes, this would be the strike-slip type shear stress, 2 times the viscosity times the strain rate of that kind. And that strain rate is 1/2 times the u, that's the x component of velocity in the gradient in the y direction, plus the v component, the y component of velocity in the x direction. And you multiply 2 by 1/2 and they cancel and you wind up with this. So what we want to do then is take these equations and substitute them into this. So here are these equations again. Horizontal compressive stress depends upon the gradient in the horizontal component of velocity in that direction, plus the pressure for both x and y, plus the shear strain rate. We're putting them into the equation of equilibrium, this gradient in horizontal compressive stress plus the perpendicular gradient in the shear stress, the same for the y component. And if we put these equations in, clearly putting du dx into this part of the term just gets you a second derivative of u with respect to x squared. Putting the pressure in simply gets you the gradient in the x direction of the pressure. And then in the shear stress, we put this term in, du dy, so we wind up with, this is a gradient in the y direction, so we wind up with second derivative of u with respect to y squared. And when we plug the v term in, we wind up with this term. And the same applies when we do the other component, the other equation in the equation of equilibrium. I'm doing this backwards. So we first do the compressive stress in the y direction, where we put in this term, so we get a second derivative of y plus gradient in the y direction. And then plugging that in, we wind up with these 2 terms. So these 2 equations then are the equation of equilibrium now expressed in terms of pressure and in terms of components of velocity, u and v. And so I've just rewritten those equations up here. Now, a second thing we can assume is incompressibility. Incompressibility means that the 3 components of compressive strain rate, the x component, the y component, and the z component, they're equal to 0. But in fact, the z component we've already assumed is 0. And the xx strain rate is simply the partial of u with respect to x. The yy strain rate is simply the partial of v with respect to y. That sum is equal to 0. That's incompressibility. If there was compression, then these 2 terms could amount to some other non-zero term. But one commonly assumes, and with good reason, that the medium is incompressible. And so we can rewrite this equation in this way. And if we take this first equation up here and we substitute for the partial of v with respect to y, let that equal minus the partial of u with respect to x, the only term that enters is this fourth term up here. So these first 3 terms are rewritten down here, the same terms. And we substitute into this and we wind up with minus viscosity times the second derivative of u with respect to x squared. Notice that this term is simply half of this term with a negative sign. So when we add these together, we'll get rid of that 2 and we'll get rid of that term there. And the same is done with the y equation or the v equation, this equation in here. When we substitute this partial of u with respect to x is equal to minus partial of v with respect to y, in here we wind up with this minus sign. And this term then cancels with this and simplifies our equations to be simply the second derivative with respect to x plus the second derivative of y of the u component plus the gradient of the pressure in the x direction. And then the same for the v, the partial of squared of v with respect to x squared, partial of v with respect to y squared, that sum plus the pressure with respect to y. This is simply saying that the pressure gradient, of course, is the force that's causing the component of v to be whatever it is in its particular direction. Now, then there's one last trick, or not one last trick, a third trick. There'll be one more trick. We introduce a stream function. This is, again, very common in dealing with fluid mechanics. The stream function defines lines along which the flow takes place. If the flow is steady state, then the flow is parallel to a constant value of the stream function. And this is written where the u component is minus the y gradient in the stream function, and the v component is plus the x gradient in the stream function. So if we plug this into this equation, if we plug u in as the partial with respect to y, clearly we're going to get a partial with respect to y up here. Clearly we're going to get these are third derivatives in the top, and this will be the third partial derivative in the y direction. In this term, both of these are minus because that minus sign is there, but the pressure gradient hasn't changed. The pressure is still the same. And when we put this in, we get the same result, effectively the same result. This term goes in, makes this a third derivative, partial derivative of v with respect to x, as we have here. We plug this in, we get a third derivative of v, now partly with respect to x and squared with respect to y, and the pressure hasn't changed. Why have we done this? We've done this because the pressure is a nuisance. We don't want the pressure. What we want to know is, what are the speeds? How is the flow taking place? What's the nature of the flow? And so if we can solve for phi, we know that flow, but we have pressure in the way. And now, again, standard trick, very simple. We take the derivative of this equation with respect to y. So we have the second partial of p with respect to x with respect to y. And we take this old equation, the same derivative with respect to x. So we have the second partial of p with respect to x and y. This term, when we've taken the x component of this equation, derivative of the x component of this equation, the y component of that equation, these two expressions for pressure turn out to be the same, and we can subtract them. So we differentiate the first with respect to y. If we do this with respect to y, this becomes fourth partial of phi of y squared and x squared. So it's this term down in here. It's minus, but we're going to subtract it from that equation. So it will be plus. It's only one of these. When we plug this into this equation, we get the fourth derivative with respect to y. It's minus, but we're subtracting it from this equation, so it comes out plus. And then in this equation, we're differentiating with respect to x. So this is the fourth partial with respect to x. That's this term. And this term is the fourth partial squared with respect to x squared with respect to y. So it's another of these terms. And we wind up with this equation. When we've done this, we differentiate this with respect to x, this with respect to y, and subtract the equations, we wind up with this. And this is sometimes written in this way as the fourth, the gradient, or the nabla to the fourth power of phi. I just write this for convenience. We don't use this. So this winds up being the equation that we must solve when we know our boundary conditions. So if we have boundary conditions, as I wrote before, if we have v moving inward at x equals 0 and moving outward at x equals lambda over 2, where this width of this region is lambda over 2. Lambda is the wavelength. So it's a cosine function like this. And we have x equals to 0, no horizontal movement along this boundary. I think this is actually, well, anyhow, I'm not going to worry. I think there's a mistake here. And in this case, we have the horizontal component of velocity moving with a sine function. So it's 0 at this corner, 0 at this corner, maximum in the middle, where x is equal to lambda over 2. Lambda over 2. And so you wind up with this being the sine of pi over 2, lambda over 4 it should be. You'll have a maximum value in here. This is very simple. Again, we're following the work of England at all. So let's start with this one. We're talking about the strike-slip boundary. This is the boundary condition. We're putting a horizontal component with a sinusoidally varying magnitude along this edge in here. We're assuming there's no vertical component along the edge in here. I think I've made a mistake. I think this is wrong, but we'll move forward. I'm now just going to give you the solution. I'm not going to take you through how you get the solution, but this is the solution for the stream function that matches this boundary condition, and of course matches with the components of velocity vanishing infinitely away. And so what do we have? We have u is equal to some u0, this same u0 at the boundary. It has the same sign of x term in here, but the magnitude decays exponentially with distance. As y gets larger and larger, the exponential goes to 0. The magnitude of the velocity decreases exponentially, but there's also another term in here, this another bracketed term in here. When y is equal to 0, of course, that's 0, and we simply get our boundary condition back here. But as one goes into the medium farther and farther for y, this means there's a change in sign. I'll say a bit more about this in a minute. I'll come back to this. And the v component, this is why I think I made a mistake. This is wrong. This doesn't look like that. So I think what I've written here is wrong. I have to fix this. The v component, this, now notice at when y is equal, oh, maybe I'm right. Y is equal to 0, it's equal to 0. And it would have this cosine varying and an exponential decay. And as y gets larger, this term will get larger, but it will decay exponentially. And notice it's got a minus sign. And that's because if you're moving horizontally in this direction, the movement will be toward the bottom boundary on this axis where x equals 0. Well, if you put x equal to 0 in here, this is 1. And hence, you have a minus sign because the velocity is downward. And if you allow x to be lambda over 2, put lambda over 2 in here, of course, this is then minus 1, cancels the minus 1, and you have rapid movement away at this point. So these equations match the conditions, and they have the interesting property that, of course, they match along the boundary and near it. The speed decreases exponentially away from the margin, but there's in fact a change in sign as you go farther and farther away. I have a picture of that, but I think that comes in a minute. I'll come back to this. Now, suppose we have this boundary condition where y moves in with a cosine x. So, well, that's what I just said in here. So the maximum y component, v0, is right here at x equals 0. When you go to x equals lambda over 2, this becomes minus 1, and you have movement in the opposite direction. So we get a stream function. We get a value for the u component of velocity where this is not 0. That's the mistake that I've made in here. And the v component looks different, looks very similar to the x component, but there's a difference. First, both u and v decay exponentially with y. So as you go farther and farther away, velocities decrease. Again, you have this cosine function as you do with the boundary condition. But here, as y gets larger, this term gets larger, even though it's damped by that term. This is different from the strike-slip condition where there was a minus sign in here. So if we compare them, for the indentation boundary where you move material in, material moves in, flows around, and comes back out as it does right at the boundary because of this plus sign. With the strike-slip boundary, movement is to the right in close, but at a distance away where y is equal to, I say approximately because I'm pointing at a point that's approximate, but where y is lambda over 2 pi in here, if y is lambda over 2 pi, this equals 1, and that term vanishes. And when you go farther away, y gets larger, this term becomes negative, and the flow is to the left. So up in this distance, you have movement to the left. In this region, you have movement to the right. So the strike-slip boundary condition and the indentation boundary condition differ in this important way, in that for one, the flow is similar at any distance, decaying exponentially away, whereas in the other, there's actually a circulation, in this case, counterclockwise circulation of the material in here. Now, the important point here is that the indentation boundary therefore affects the deforming region much farther into it than the shear boundaries. The shear boundary, you go to 0 in here, and then you have a bit more deformation, but the exponential decay term is killing that out. And here you feel the effect of the indentation much farther into the region than you do with the strike slip. I'm going to come back to this because this is also the case with non-Newtonian viscosity. So we've just covered the simple case. Deformation is a function of distance from the boundary. Now let's let there be a non-Newtonian, non-linear constitutive relation, non-linear viscosity, where strain obeys an equation like this, strain rate. Strain rate obeys an equation like this, where it varies with some power of the shear stress or with the deviatoric stress, however you've defined it. This is a much more complicated problem. I'm just going to give you the answer. So let me state at the beginning, the wavelength again sets the scale. But in this case, if you have an indentation boundary where you're pushing in here and you're pulling out over here, and of course there's the symmetry, so over here you're pushing weaker and weaker and it decays away. In this case, again, you have the velocity, the y component of velocity pointing upward here, has this cosine variation in the x direction, but it decays exponentially with y, with some characteristic constant in here. The same is the case with the x, with the shear boundary. If you have a shear boundary moving along in here, you'll have shear that will decay exponentially and get weaker and weaker as you go farther away. Again, decaying exponentially, but with a different decay constant. The y in here is different from this one, and I'm just stating this is the way it works out. The y normal decay is 4 times the y strike slip. In other words, this decay is 4 times slower going away from the boundary than this decay. And therefore, if you have indenting boundary conditions, you should reach deeper into the material than if you have strike slip boundary conditions. And I remind you, if it's Newtonian viscosity, the equations are a little different because of this plus sign and this extra term, this minus sign and this extra term, and this counterclockwise flow. With the non-Newtonian viscosity, you don't have that counterclockwise flow. You never have that. You just decay away more and more as the distance gets larger in this case. Okay, well, let's consider different kinds of lithosphere. Let's go back to oceanic lithosphere, where you have thin crust. The strength increases essentially linearly because of friction, and then at some point, of course, there's not a sharp corner here, but we won't worry about that. Then when the material's hot enough, you get plastic deformation or viscous deformation, where because of increasing temperature with depth, the strength decreases with depth. And this is the equation that we had last week for Peierls creep. Complicated equation. Strain rate varies with some constant times a stress times some not very large exponent, then times an exponential that depends upon an activation enthalpy divided by the ideal gas constant and temperature in kelvins, of course, with a negative sign here. Negative sign because if temperature is large, this becomes small. The exponential of a small value will give you a strain rate. But if this becomes a small value, if temperature is small, this becomes a large value, and an exponential of a minus large value will be a small number, so the strain rate would be smaller in the case of low temperature than high temperature. And then one has this complicated dependence where sigma is the differential stress. It's effectively the deviatoric stress. It scaled by some background stress raised to some power, and then this difference raised to a power. Many of the flow laws are 0, P is 1, Q is 2. So we can simplify this equation by making those substitutions, letting P be 1, getting rid of the term in here that depended on stress to the power R. If we let R equal 0, that goes to 1. And I should point out that the strain rates are much smaller than this value. That's another way of saying this exponential factor is large. It is not large. It's smaller than 1, and it goes from being of order 1 to much smaller than 1. And I should point out that the ratio of the activation enthalpy for piles creep is of order 20 times the product of the gas constant and the temperature. So this is a big factor in here. An exponential to a big factor negative means this quantity is going to have a small value. It's going to be less than 1 is really what I want to say. Now, this is an ugly equation. One can turn this around and write stress, deviatoric stress, in terms of strain rate, where strain rate now appears down here. All I did was divide by this, take the logarithm. Here's the logarithm. The logarithm of this, of course, is then this factor. Then divide by that. It's there. Subtract, take the square root, and just manipulate this around. This isn't interesting. This is the equation, and this factor in the square root is smaller than 1, so we have sigma minus sigma e times a number smaller than 1, so this number is positive. It turns out, looking at this, if we take this equation and first just look at temperature dependence, these are plots, the logarithm of the strain rate, of the stress, sorry, it says tau in here, but it could be sigma. I'm assuming they're the same, as a function of temperature, though in this case it's plotted as inverse temperature increasing in this direction. So I've replotted this for you. 500 kelvins or 723 degrees Celsius or 1273 degrees Celsius. This is almost a asthenosphere at this temperature out in here. And these are the strain rates, and you see there's almost no dependence on the strain rate. This depends on temperature, but not strongly on temperature either. In other words, this value is weakly dependent on temperature and even more weakly dependent on strain rate. This is the definition of a plastic medium. And if you take this equation and say, well, let's fix the temperature. So fix the temperature at 700 kelvins and simply plot the log of the stress of this stress versus the log of the strain rate, this over here, this is a straight line. This fits a plot like strain rate varies as stress to some power. This is what we've been assuming, except the power is very large. N is 26 for 700 degrees, N is 17 for 800 degrees, N is 11. 11 is a large number for 900 kelvins. So the point is that this equation is a good approximation of this equation, though it depends, it varies, the value of N would vary in here. So if we go back and we say this equation actually behaves like this power relationship between strain rate and stress, but with a very large value of N. This is like a perfectly plastic material. A perfectly plastic material, there's no deformation until the stress reaches a yield stress, and then strain occurs at a constant rate. That's the definition of a plastic material. And moreover, the strain rate is at most weakly dependent on temperature. It really doesn't matter very much. So let's look at a place where we can apply this. Again, we're looking at oceanic lithosphere. And we're looking in the region between the India plate up here and the Australia plate down here. Originally, these were considered one plate, but there's a lot of earthquake activity within this corner between the India plate and the Australia plate in this area. Very large. This is the largest intraplate seismicity in the world, the biggest strike slip faulting, in fact, in this area. And if you convert this seismological evidence into a strain rate, you get a strain rate pattern that looks like this. This is the north-south component of strain rate. Compression is shown as negative in this case. So this blue is negative. This is compression. Extension would be red up in here. These arrows are showing the orientation, or actually the relative, I think it's the orientation of the principal stresses in the region where they come and they become compressive in here. I've forgotten what they mean. And this is the bathymetry for that part of the world. The bathymetry shown over in here. This is the region of this very high strain. And this is the geologic strain rate, about approximately 1% per million years, or 3 times 10 to the minus 16 per second in this area. This is not a high strain rate for a plate margin, but it is a high strain rate for an intraplate region. And what they did was they solved for the value of n, fitting the deformation in this region by imposing the relative velocities of the India plate and the Australia plate, and then they fit the rate of thickening. Now, thickening they're treating as positive. So this is a region where you'd have compression, negative in blue, and thickening, now they do with red. I think this is unfortunate, but this is the way they've done it. So bright red here corresponds to bright red blue over there. And they're thickening, and notice how the locus of thickening varies with n. N equals 1, n equals 3 here, n equals 10 in this case, n equals 30, and n equals 100. And the n equals 30 matches the compressive strain best. This is the value they liked, n equal to 30 in here. This is a very large number, n equals 30, I remind you. So if we go back, and just back to this equation that we had before, it behaves as if strain rate varies as deviatoric stress to the nth power. And for this region, n is large, very large, n equals 30. This is like a perfectly plastic material. The lithosphere, the strong continental lithosphere, behaves as a perfectly plastic region. Now let's consider the jelly sandwich. The jelly sandwich is more for a continental region, a strong-forming continental lithosphere, where you have brittle strength because of slip-on faults at shallow depth. Then the crust is weaker because the minerals of the crust can flow, but the mantle can be strong. Olivine is stronger than the crustal materials. And so the strength would largely be in the mantle in this case, or in this cartoon version. I showed you this last week from Björkman and Dresden. So again, strength increasing because of brittle, then weak because the feldspars and the quartz are weak. So you have this weak zone in the middle, the weak zone shown over here. And then the strength is in the mantle down in here. And because the strength is in the mantle, and olivine in the temperature range that would apply here, which is not where Peierls creep works, is more where dislocation creep works, n is going to be of the order of 3 to 3.5. This is what we would expect for this situation, that we would have a value of n equal to 3 to 3.5. And I go back and remind you that the deformation, if you have indenting boundary conditions, the decay with distance, y normal, is much greater than it is if you have decay of strike slip reaching in here. And in fact, I think I didn't show you this before, but the value of this exponential decay constant depends on the wavelength, of course, the width of the deforming zone, but it also depends on the value of n through the square root of n. And the normal condition, notice, is 4 times larger than the strike-slip boundary. The strike-slip boundary, this decay constant, is reduced by this factor of 4. But again, you have this square root of n. I didn't derive this. I just told you this is the case. This comes from their work. This is a beautiful piece of work. So the strike-slip decays more rapidly with this factor of 4, but the decay rate itself depends on the value of n. In both cases, that's the case. And so if we look at this, the boundary, the strike-slip boundary, 2D layer with a nonlinear viscosity and strike-slip, nonlinear strike-slip viscosity. I don't know what I was writing in here. This doesn't make sense. I'm sorry. It's strike-slip shear, and it's nonlinear viscosity, n varying with stress to the, the strain rate varying with as stress to some power n. The deformation decreases exponentially with distance, again, where now L is the we're going to let L be the width of the boundary that's imposing the strike slip boundary condition on the deforming medium. That's essentially half the wavelength. And we have this equation again where U0 is the velocity on the boundary, the strike slip component. We're letting it vary sinusoidally. It decays exponentially, and that exponential decay constant, we've now changed our definition. This is not lambda anymore. This is L. So this is the 4. There was a 4 down here. There's now just a 2 with the square root of n. And as an example, if n is 3 and the boundary were 500 to 1,000 kilometers long, then we would expect this decay constant to be of the order of 50 to 100 kilometers. Not a large distance into the region. The point here is that deformation for this case occurs over a relatively narrow zone. And as an example, the Basin and Range province of Western United States, big, large area out in this area, bounded on the west by the block of the Sierra Nevada. The Sierra Nevada mountains of California act as a rigid block. They lie east of the San Andreas Fault, so the Pacific Plate is out here. The Sierra Nevada are essentially a rigid block moving a little bit more slowly, a little bit more rapidly than California relative to the Pacific Plate. So they're moving northwest. They have a bit of motion relative to the region out in here. This is a plot. Well, let me look at this plot first. These are GPS velocities. So this is going through, you can see the outline of the state of Nevada in here. That's this same state over in this area. And you can see these are velocities relative to North America. So they're very small over in this area, and they become faster and faster. And then they're essentially constant through the Sierra Nevada, and they go out, and then they become very large near the boundary relative to California. These, or I should say, on the Pacific Plate. Once you're on the Pacific Plate, then you're much faster. This is a plot now of the component of velocity parallel to the motion of the Sierra Nevada relative to North America. So this is much smaller, only 10 millimeters a year. And this is the distance. 0 in this case is the edge of the Sierra Nevada over here, the edge of the Sierra Nevada coming through here. And so these velocities then are decreasing, this component parallel to the motion of the Sierra Nevada. These decrease as you go towards the northeast. There's a slight step in here when you get near the eastern edge of the Basin and Range. But you can see there's a speed up in here, and you can fit this with an exponential. So all of these curves are curves of an exponential form, but using different values of this characteristic distance, this decay distance in the exponential, where L has been set at 600 kilometers. And if n is 1, Newtonian viscosity, the decay is too slow. If n is 15, the decay is too fast. Some data are fitting n equals 9, but most of the data are fitting the region between 3.1 and 4.6. And if you plug in n equals 3 into this with 600, this decay distance is 55 kilometers. And you can see if this is our 0 point here, when you've gone 55 kilometers, you're down by a factor of roughly 2.7. And when you're out to twice this distance, you're down by even more. So this exercise is suggesting that n is of the order of 3. It's in this range of 3.1 to 4.6. Hence, the mantle is contributing. The mantle and viscous deformation, maybe in the crust, are contributing large fractions of the resistance to the deformation, the viscous strength of the mantle, and maybe some of the crust. So now, if we consider, again, I've been sloppy. I can't tell you how many times I've corrected this file, but anyway, I've got mistakes in here. We're considering a convergent boundary in here, again, with nonlinear viscosity, strain rate varying as stress to some power n, again, repeated down in here. The deformation decreases exponentially with distance from a boundary of length, given L, let it be pi over 2. So if we plug this in to this expression, we have this exponential decay where we have some characteristic y normal distance. That y normal distance here now is 4 times bigger than for the strike slip case. Here the 2 is in the denominator. Here the 2 is in the numerator. This is the case here. This is the case we just looked at. And if you put n equals 3 and let L be large, 2,500 kilometers, then the y normal component, the decay, is of order 1,000 kilometers, 900 kilometers. And so if we look at Tibet as an example where deformation occurs over a wide zone, it's something like 4 times bigger than strike slip. Here's the going from the western syntaxis to the eastern syntaxis of the Himalaya. This is about 2,500 kilometers, and Tibet reaches in of order 1,000 kilometers in this area. A little further over here, a little less, but then you have the Tian Shan up in here. So the point again is that the deformation reaches much deeper into a region where the boundary condition is indenting than where the boundary condition is strike slip. And if we go one last step, suppose that most of the strength is in this part, in the brittle part. In other words, we go to a creme brulee, where the mantle is so hot that the olivine provides very little resistance, and most of the resistance is brittle deformation in the crust. I take this, here's a paper, creme brulee, right there in the title. Bergman was one of the people who coined the term, but this is an analysis of GPS velocities after 2 large earthquakes that occurred in eastern California. So the San Andreas Fault comes down through here. Here's a map of California, and you see this block. And these earthquakes occurred out in this region, and they caused deformation. They caused a change, of course, in the stress. Suddenly, with slip on a fault, there's application of stress. You've changed the stress in the surrounding region, so the surrounding region deforms. These colors are showing contours of strain rates. We won't worry about that here, but this is a region that continued to strain for many years after these earthquakes, which occurred in 1992, 1999. And when they solved for the viscosity structure, assuming an upper layer that's elastic, an elastic upper crust, a viscoelastic lower crust, so the lower crust is both viscous and elastic, and the upper mantle is viscous and viscoelastic, they inferred that all the strength is in the top, that the viscosity in the mantle is actually quite low, 4 times 10 to the 19 Pascal seconds. So the mantle is weak. And if we look at this, the background strain rate in this region is not small, but it's not great. 1/10 of a microstrain per year, 1/10 of 10 to the minus 6 per year. If we convert this into seconds, 1 year is 3.16 times 10 to the 7th seconds. So we get this for a strain rate in seconds. Remember, viscosity, 4 times 10 to the 19th. Stress is 2 times viscosity times strain rate. We multiply these together. The stress is 1/4 of a megapascal. Stress drops in earthquakes are typically more like a megapascal, and very rarely are they as small as 1/10 of a megapascal. This is a small stress. Earthquakes, the stress drops. The stresses on the faults may be bigger than this. So the point is that in this case, the resistance is greatest in the brittle region, not in the viscous region. This is a case where all the strength lies up in here. And if we take this one step further, as I said, a plastic material, if you raise the stress until you get the stress large enough, there's really no deformation. Once you reach a yield stress, then it flows. So this is strain. If you get to this point, strain just increases. Well, with earthquakes, you increase the stress drops. You increase the stress drops. You increase, stress drops during an earthquake, increase during an earthquake, drops during an earthquake. The background stress stays quite constant. So in some sense, in this case, the material occurring with repeated earthquakes, the stress that acts on the faults is behaving like a plastic material. So recurring strain accumulation and release by slip-on faults during earthquakes creates an effective rheology that's like a perfectly plastic material. Once the yield stress is reached, strain occurs steadily at a constant rate, forgetting earthquake recurrence intervals. In sense, it behaves this way, but with n approaching infinity. N as infinity would be the perfect plastic case. So I want to quickly now just take you into different topic altogether, seismic anisotropy. Isotropy means the same in all directions. Anisotropy means different in different directions. And so P waves, which are longitudinal waves, can propagate faster in some directions than in others if the material is anisotropic. And S waves, which are transverse waves, like light, the speed of propagation depends on polarization, and waves with different polarizations propagate faster than others. The key here is that anisotropy provides a, albeit crude, strain gauge. And just to remind you, another term for anisotropy in this case would be birefringence. And many of you have looked through a calcite crystal. This person is holding a calcite crystal, and you can see a double image through here, two images, because the speed of light polarized in two directions is different, or the speed of light in one polarized one way is different from the speed of light in another. Same thing, here's a black line with the word calcite written underneath, and you see the word repeated because the two wave speeds are different. And then a nice, this is the prettiest of all, this little jewel that's been around. When you look through the calcite, you see two images because the two polarizations are propagating at different speeds. Well, if you look at strain, we can talk about pure shear, where we have a circle and we squash it and stretch it, squash it, stretch it, squash it, and stretch it. This is pure shear, squashed in one direction, stretched in another, or simple shear, where we apply a strike slip like boundary condition, stretch it and rotate it, stretch it and rotate it. We wind up with these shapes, these strain ellipses. The maximum elongation, I mention this because this is important in the seismological analysis for olivine. I should say not for ice. Ice is very different. Ice is also anisotropic. The maximum elongation is clearly in the direction where the strain ellipse is stretched the most. So the maximum elongation is shown by these blue lines. And this is important because for olivine, I'm emphasizing this is olivine, the fastest direction for P wave is parallel to this maximum elongation, and the slowest is perpendicular to it. So in this case, the fastest direction for P waves would be along this line, and the slowest would be perpendicular. Speeds, I'm talking about speeds. P wave speeds are fast this way, slow in this direction. And for polarization of S waves, imagine an S wave coming out of the screen. The S wave is coming toward you. The S wave that's polarized horizontally here is faster than the S wave that is polarized in the Y direction with this orientation. The S wave polarized with this orientation is faster than the S wave polarized with that orientation. And this is a nice animation made by Ed Garnero that I took off the web. Imagine this block is anisotropic. The fast orientation is shown by this flat plane, and the slow orientation is the vertical in here. The S wave comes in oblique, and you see the S wave then speeding up. The quasi S wave that's faster is the blue one, the red one is the slower. And this is what one sees with the seismograms. One sees these S waves split into two quasi S waves that travel with different speeds. So an S wave encountering an anisotropic layer, the S wave will be split into two quasi S waves. The one polarized parallel to the maximum elongation propagates faster than the one polarized perpendicular. And this is saying kind of the same. Orientations of polarization of fast quasi-S waves and shear wave splitting and fast propagation of P waves are parallel to the maximum elongation. Well, if one goes into the lab and measures this, one can strain olivine. And this is a plot, this is a little confusing, or confusing for me too. This is the angle between a certain orientation of the olivine crystal and the orientation of shear. So we can look at this as the orientation in the crystal, this is the orientation of shear. And as you strain this more and more and more, what happens is the strain ellipse, of course, stretches, and the orientation of this 100 plane or direction rotates around and becomes smaller and smaller. This plot is this line shown right in here. That as you increase the strain, you also you change the orientation of this peak. It starts at 45, random orientation, and it becomes closer and closer to the orientation to the plane of the shear itself. The plane of the shear is horizontal in this direction. And the magnitude of strain is shown down here. That's 100% strain. 100% strain is probably a pretty good approximation of maybe I'm wrong. Maybe this one is 100% strain. But these are large strains. These dots, plus signs, circles, squares, triangles, these are laboratory measurements. And they're essentially saying that the strain, the orientation that you get when you strain the olivine is faster than if it were just simple shear. You are rotating these around faster. And if one takes those that are aligned parallel to the sense of shear, this is a case where this 100 peak would not be aligned that way, but would be aligned this way along in here. This is dynamic recrystallization. The crystals, the crystals of olivine recrystallize with a new orientation, and they become parallel to the sense of shear. It's as if this suddenly snaps into place, where you deform this, and then this maximum elongation suddenly snaps into is parallel to the plane of shear down in here. And so if dynamic recrystallization occurs, then the fast orientation becomes parallel to the shear zone. And in the laboratory, this is showing layers of pyroxene. You can kind of see hints of layers in here where they're bent into a shear zone in here. This part of this rock outcrop, this is an outcrop of rock tilted on its side, by the way. The up direction is to the right. And this is now showing how these layers are bent around, and then looking at the orientation of the 100 plane in these crystals, how they're bent around, and they're bent, the lines in here are showing you this. This is, again, is simple shear where everything is bent around on an outcrop scale. You can see this anisotropy here. Well, if we go to the Earth, and next week I'm going to describe this for New Zealand, because New Zealand is a very good example. If you imagine a zone with strike-slip faulting at the surface, and hence shear, simple shear at depth in the mantle, so you have simple shear down in here, the strain ellipsoid would be aligned parallel. There's so much strain, and there's dynamic recrystallization, that the maximum elongation would be parallel to the strike-slip faults up in here. So Pn, the P wave, would travel fastest along this parallel to the faults and slowest perpendicular. Whoop. And an S wave coming out of the deep Earth, an S wave, a seismogram like this, would go into this anisotropic region, and the faster of the quasi-S waves would be polarized parallel to the faults, and the slower would be polarized perpendicular. So one can measure crudely the strain that's occurring that gives rise to this anisotropy. And just one example of where this has been done, I just pulled this out mostly because it's near Colombia. This is the Merida Andes over in here. The Caracas would lie over here, Venezuela. This is the Colombia-Venezuela boundary over in here. Colombia, of course, over here. And if one looks at inferences of anisotropy made with the separation of the two quasi-S waves, shear wave splitting, up in this region where you're near the boundary between the Caribbean plate, which moves eastward relative to South America, the lines are showing you the orientation of the faster of the quasi-S waves, the earlier arriving ones. So this is the orientation of anisotropy, if you like. And it's parallel to the plate motion, as one would expect with large strain. In the Merida Andes, where you have the Boconó fault, a big right lateral fault in here, the maximum the orientation of the fastest shear quasi-S wave is parallel to the fault, northeast in here, at all of these stations. And I should say the magnitude, the length of the line is proportional to the magnitude of the time between the two quasi-S waves, which is proportional to the degree to which the upper mantle is anisotropic. Now, if you go into the Guiana Shield, you still have anisotropy. Presumably that's because these are frozen into Precambrian lithosphere, and it's been anisotropic for a long time. That's my presumption, at least. So if I summarize, if we have a deforming continental region, the distance reached into the deforming region scales with the width of the boundary where the stress is applied. That makes sense. The deformation due to indentation reaches roughly 4 times deeper than a strike slip shear boundary condition. Where strain rates vary as a deviatoric stress raised to a power n, as in the case of strain rate to deviatoric to power n, the distance into which the deformation reaches scales as 1 over the square root of n. So if n is a big number, the deformation reaches a short distance. If n were 3, it reaches a smaller distance into the material. Oceanic lithosphere behaves as a nearly perfectly plastic material where n is of order 30 in this relationship. For continental lithosphere, if it's strong, the strength is concentrated in the mantle, and it deforms, again, with typical dislocation creep values, where n is of the order of 3. But if you're in a weakly deforming continental lithosphere, slip-on faults can be the main resistance to deformation. And insofar as we can use this approximation, again, n is greater than 3, but much, much greater than 3, and approaching infinity if slip-on faults determines the results. And finally, finite strain creates anisotropy, which can be measured with seismic waves. And seismic anisotropy therefore provides a, albeit crude, strain gauge. And I hope I didn't go too fast, and but I'm now finished, Hector, and I turn it back to you.
Thank you very much, Peter. Although for the mathematics formula today, I saw that. Well, I think I don't see any questions so far.
Okay. Okay. I hope I didn't put everyone to sleep.
Well, how is possible to interpret that? Maybe everything is very clear.
Well, as I told you, you're polite.
Ok. Muchas gracias a todos. Nos vemos en la próxima sesión, el próximo martes, para continuar con lo de Nueva Zelanda. Cordial saludo a todos. Muchas gracias. Buenas tardes.